So this is primarily the work done by Garth and I. Yeah, well, you can read. Okay, so this is the outline of the talk, so it's in 2 parts. So first I'm going to talk about quadrature representation and the optimization of this quadrature representation, which is sort of work already done and completed until Anders told me there's a bug in quadrature representation for netlog elements, but okay, I guess I have to fix that. And then the second part of the talk is the implementation of lifting formulations in FEniCS, or potentially future work anyway. Okay, so let me start here with the quadrature representation. So if we take a model problem, so the weight Laplace equation and the bilinear form and the UFL equivalent, we see it's pretty simple. And we can represent that in FFC in 2 different ways. One is using quadrature, which is basically just a bunch of loops. We have the loop over quadrature points, some loops of the spatial dimensions, loop over the degrees of freedom for the function W, and some more looping, multiplication by the determinant of the Jacobian and the weight at the quadrature point. We can also use tensor contraction representation, which is pretty much, well, it is a tensor contraction between a reference element and a geometric element, and the reference element can be computed before runtime because everything is defined on the reference tensor, and these geometry terms we need to compute at runtime because it's dependent on the information from the cell. But I'm sure that people in the audience that can explain all this much better than I can, so I won't go into details with that. Just mention that tensor contraction was the original representation for tensors in FFC, and then we extended or added this quadrature representation, and it was motivated by problems like plasticity, which is pretty simple actually. The form is not that difficult. We just have this is the symmetric gradient in Voigt notation, and then we have a tangent, a consistent tangent which has 36 components because it's a 6x6 matrix. And here we just have the bilinear form. So when we compile this with the original FFC, we had to sit around and wait for it for like 4.5 minutes, which is pretty long if you're in a hurry like Garth is. And the output of the generated code is 11 megabytes, which is quite large actually. And when you try to compile this with C++, then it takes forever. And the number of operations, however, is pretty good. So we implemented this quadrature representation, which is pretty much, at least initially, just dumping all the loops into a header file. So we resolved this convolution time problem. So we got down to 2 seconds. And the code is very compact, but the number of operations sort of skyrocketed, which is not very good. I was not pleased with that. So we did some optimizations on this quadrature code or the output, and we got down to 106,000 operations, which is pretty good. So an improvement of the order of a factor of 30. So we're quite happy with that. So how do we do these optimizations? Well, basically it's just 3 simple things. So tabulate the basis functions, and we eliminate the floating point operations on zeros, and we do some loop invariant code motions, and I'll explain all that in detail just in a second. And we describe all this in this paper here that hopefully will be accepted soon. So here we have the generated code for the tabulate tensor function for the weighted Laplace equation. And first we tabulate the quadrature weight. So quite simple actually, but okay. And these are the basis functions for the function W evaluated at this quadrature point. So we have 3 nodes and therefore 3 values. And the derivatives of the basis function is -1, 0, 1, and -1, 1, 0. So we skip the 0 and compress it a bit, so we only have 2 non-zero values, but then we need to store the information on where those non-zero values are located, so we have 0 and 1 and 0 and 2. Then we compute everything which is constant, so independent of loops. So typically it will be the geometry terms, the determinant, but it could also be constant functions if we had that, like discontinuous constants. And they would also be included in these terms. And then we loop the integration points. So the first thing we do is to compute the value of the function w, so we just sum over the nodes, the dot values, times the basis functions, and then we compute some auxiliary constants which are constant within this loop, so the loop over the indices of the basis functions of v and u. So actually for each entry we can then compute each entry in 3 operations. So if we count this as 1 anyway, so 1, 2, 3 operations. And notice that we need to map the value computed for this entry to the correct position in the local finite element tensor using those arrays of integers, right? So the good thing here is that we go down from a 3x3 loop to a 2x2, so that's effectively a factor of 2. And for complex forms, this reduces quite a bit. So if we look at the performance for forms of increasing, or I should say varying complexity, and if we define a simple form, which is an elasticity-like form, so a symmetric gradient here, and we pre-multiply it with a number of functions, and we have different orders for the basis functions of v and u, and also a different order of the pre-multiplying functions, and we vary all that. And we see here the results, so this is the case that we had before. And we count the number of operations for the tensor contraction, and we compare that to the number of operations for the quadrature representation, and in this case, tensor contraction is around 40% faster or something compared to quadrature. So you would expect this to be faster using tensor contraction to evaluate the local tensor, only the problem is that the code generated will be 96 megabytes, and I was not able to compile it, so I went for quadrature representation for this case. Okay, so we have all these numbers, but there are only 3 major things to really notice about it, and that is that if we look at this block, for increasing values of q, so the order in v and u, so the test and trial functions, tensor contraction is better. But if you increase the number of pre-multiplying functions, it works in favor of quadrature representation. And if we increase the order of the pre-multiplying function, we see that it also works in favor of quadrature. So
what is the threshold? Because we're thinking about this choosing a value of n.
Yeah. So let me just quickly show this. So what we basically did was we increased the usability of FFC because we increased the range of problems that we can tackle, and it's a complementary to tensor contraction because for some forms we see here that tensor contraction is much better, but for other forms like this, quadrature representation is a lot better. And then we have cases like this where it looks like tensor contraction would be best, but then because of the size of the generated file is so huge, well, you can forget about it anyway, so you should still pick quadrature. Yes?
Yeah, you should be able to just query, if you have an object in Python that represents the form, you ought to be able to query it based on the quadrature rule, the number of forms, the number of derivatives.
Yeah.
Just go through the multi-indices, and you ought to be able to actually have FFC calculate that.
Yeah. So just
before it generates anything.
Yes, that's a key thing, before generating anything, of course. So let me just add to that, is that we need to get this estimate quite accurately, so within 5 to 10%, because if it comes out that one is better than the other, and then in the end you see that when you actually run it, that can still be quite a big a big difference. So it does make a difference whether you choose one over the other. So you also need to take into account some cutoff limit, I think, for when the file size will simply be too big to compute or process by the C++ compiler. Anyway, so yeah, this is a question mark for future work related to this, is if we can choose this representation in an automatic way. Okay, so let me proceed with the next part of my talk. So this is a Poisson equation using a discontinuous interior penalty formulation. So this is what we have in Dolphin demo. And we see we have a test and trial functions, V and U, and everything is defined directly in terms of V and U. We have the integration of interior facets. We have the jump, which is the value of the test function on one side, for instance, multiplied by the normal vector on that side.